All right, this is a practice test, and one of the questions on here is a little harder than what I'd want to put on the real exam, but it works like this. So we have this mass on an inclined plane, so we have an inclined plane problem. This is 2.4 degrees, and let's draw a force diagram here. So we're going to have a reaction force, a weight, we have the friction force, we have W sine theta, and we have W cos theta, and we want to know if this block's going to move. So what we basically want to know is W sine theta minus the friction. This is the equation we want to set up. And then, of course, in the other direction, we have R minus W cos theta balances. Now, this is only going to move if this force here is bigger than the friction force here. So we have 6.3 times the sine of 2.4, and we need to multiply that by 10, so that's 63 times the sine of 2.4. And then the friction force is going to be, friction is 0.032 times the mass, which is 6.3, times g, which is 10, times the cosine of 2.4. So let's do our math. So 63 times the sine of 2.4 times. I'm just converting this on my Mac. Well, okay, so let's just double check that. Yes, dividable. So we're talking about 2.63 newtons here. So that's 2.63 newtons for the W sine theta force, and let's compare that to the friction force. And it looks like the friction force is 2.01 newtons. So this is indeed bigger, so yes, it will slide. This one here. I really don't like this drawing, and they should have been really clear that this is happening in the horizontal plane. So here's how we're going to need to do this. This is actually resting on a table. We're looking at it from above, and they really should have been more clear on this, and I don't like that they did that. So this is going to be 4 cosine of 30. Sorry, 4.0 cosine of 30 degrees. This is going to be 4.0 sine of 30. And then this 45, we're going to have 6.5 sine of 45. And then here, 6.5 cosine of 45. So basically, we're going to get acceleration in two directions. In the x direction, we're going to get that 4.0 cosine of 30 minus 6.5 cosine of 45 equals 25 times a in the x direction. And then in the y direction, we're going to get that 4.0 sine of 30 minus 6.5 times the sine of 45 equals 25 times a in the y direction. And we can get these two accelerations, in fact. So when we actually end up doing that, what we'll end up getting is we'll get an acceleration of negative 0.025 meters per second squared in the x direction. And in the y direction at the same time, we get an acceleration of negative 0.10 meters per second squared. Again, I'm glad to assign this on a practice test, but you won't see anything like this on the real test, just so you know. All right, so now let's move on to the multiple choice, paper one, so which is a scalar quantity. Acceleration is not. Momentum is not. Any field is not. It is power. I wouldn't want to assign this one. So it's a good practice one, but not one that I'd put on there. Now, we want the displacement from P to Q. So if this is A here, this is A. This displacement would be A radical 2. And we're going southwest. All right. Constant velocity, net force, 0. A stone falls towards Earth. The force that the stone exerts on the Earth is exactly equal to the force that the Earth exerts on the stone, Newton's third law. Here, 5, we have a lamp, and we want to know what the force F is equal to, so let's be clear. This is mg, and then we have this tension here. Let's be clear, though. We got to be careful on our thetas. This is actually t sine theta by SOHCAHTOA, and this is t cosine theta by SOHCAHTOA. So F is going to balance t sine theta, and we're going to get t over sine theta as the balancing force. Careful because the angle is here. Is in a new place. And then for number 6, we're pushing this car. It's a constant force, which means a steady acceleration. So at the end of 4 meters, the car ends up with a speed of 2 meters per second. And then she only pushes with half as much force. And we want to know what distance you need to push to give 2 meters per second. So let's just be clear. There's no time given, so here's what we'll say. We know that v squared is 0 squared plus 2 times a of Marcella times 4, that's s. And so v here is 2, so we're saying 4 is 0 squared plus 8 times the acceleration of Marcella. And so we're getting Marcella's acceleration is 1/2 meters per, is 0.5 meters per second squared. That's Marcella's acceleration. And then we're going to end up having half that acceleration here. So we want to know what distance we get. So we get 4 equals 0 squared plus 2 times half of Marcella's acceleration, because it's half the force applied, so 0.25 times the new s. So we're going to get 4 divided by 1 is s, so we end up getting 4 meters for the pushing force. And then for number 7, this is one we'll skip until a little bit later on. Here we project a projectile horizontally from a high tower and want to know the vertical velocity as it falls. It's going to gain speed at a steady rate, just like in C. All right. Now, we drop an apple on the moon and we want to know the time. So on Earth, the falling is going to be 1/2 gt squared, and that time is going to be 2s over g under a square root for time on the Earth. Now let's compare that to time on the moon. S is still going to be 1/2, then g over 6 times t moon squared. So we end up getting 12s over g is t moon, and we put that under square root. Sorry, 12s with the g on the bottom. And when we compare this time to this time, what we see is that t moon equals square root of 6 t Earth. All right. So Maria pushes a book. We get the weight, we get the upward force. So let's just kind of be clear here. Let's just look at the forces on the book. So we've got the force of the hand, we've got the reaction force from the ceiling, and we have the weight of the book pointing down. So we are told the book weighs 20 newtons. We are told that she pushes up with a force of 25. And that tells us that the reaction force from the ceiling is 5 newtons to balance it out. So that's the force of the ceiling on the book. So that rules out these two. And then here We know the book in her hand, well, that's not going to work. So it's right here. Book in her hand is 25. This is the force on the hand from the book, 25. Ceiling book, 5. All right, so that's it for this practice exam. I'm going to publish the results on Haiku now.